Today's speaker is Alex Borisov from Binghamton, who speaks on locally integer polynomial functions. Please.
Well, thank you very much, Mel, for the invitation, and thank you all for coming. Really glad to get this opportunity to speak about these local integer polynomial functions. Now, half a year ago, I wouldn't even know what that is because I didn't think of the subject. I mean, they were always there, but I really got interested in that actually due to the work of my student Sayak Gupta, who is here, I think, and he gave some talks at the seminar as well. So here is the main object. Let's consider integer-valued functions on the integers with the property that when you restrict to any finite subset, they can be given by integer polynomials with integer coefficients. This would work for integers or for a subset of integers. And if X is such subset, we will call these functions lib functions on X with the notation lib of X, or in case of X being Z, we'll just say LZ locally integer polynomials of X to indicate the variable if we care. Now, if X is finite, this is really not interesting because we just take Z of X and quotient by X minus X sub 1 and so on X minus X sub n. The real story is about infinite X, even though in the definition it's about finite subsets. Now, when you have a finite subset and so of inputs and outputs, there's interpolation polynomial, which is the unique polynomial degree up to n-1. And theoretically, you might think, okay, maybe the interpolation polynomial is not in Z of X, but there is some other polynomial that is in Z of X that takes the same values. However, this cannot happen. Indeed, every other polynomial will be the interpolation polynomial plus some G of X times the product X minus X sub i's. And if G of X is not in Z of X, just take the highest degree with a non-integer coefficient, and you get in this, when you multiply by this X to the n plus and so on, you get a not integer coefficient in a degree higher than or equal to n. And so the overall polynomial will not be in Z of X. So G of X has to be in Z of X for the whole thing to be in Z of X. And so because of that, the interpolation polynomial must be in Z of X. Okay, so that's a simple but useful remark. Let's move on. Now, we're talking about restriction of F to subsets. Now, one element subset, nothing to talk about because we are only looking at functions that take integer values. For two element subsets, the restriction, easy to check, boils down to A minus B dividing F of A minus F of B. Okay, that's a good property. Of course, it's much weaker than overall lib condition, but because of that, we can actually extend our function to a function from the profinite completion, which is basically the product of p-adic integers for over all primes p by Chinese remainder theorem. And well, moreover, this function f is actually Lipschitz in a sense. To be precise, is given coordinate-wise by one Lipschitz function because the norm of the difference of values is always less than or equal to the norm of the difference of inputs. All right, so far so good. How many of these guys are there? Well, the answer is actually many. Here is a theorem. Once you see the statement, you'll realize the proof, so to speak. If you suppose we have any bijection from natural numbers to Z, and any sequence of integers, then we can cook up a local integer polynomial function on Z by the following recipe. Just say a sub 0 plus a sub 1 times x minus the first integer, plus a sub 2 times x minus the first times x minus the second, plus and so on. It's a formal sum, but for every integer, only finitely many terms will be non-zero. So you get an actual integer valued function. And it's easy to check that first it's a locally integer polynomial function. Second, these coefficients are uniquely determined by the function. Why is that? Basically, you can just see how the kth coefficient is obtained from the value of the function, the corresponding point, the previous point, and the previous coefficients. And so that's where the uniqueness and existence comes into play. And then they have to be integers so that the partial sums, which are really are the interpolation polynomials on some subsets, are in Z of x. And you can do it for any bijection. Our usual bijection would be when we count integers 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on, which we'll essentially use at some point. But this would work for any bijection. Any questions so far? All right. A few more remarks. So different bijections lead to different sequences. And since we're really talking about a basis of sorts, it's good for addition. If you want to add, you just add the sequences. Multiplication would be terrible. At least I don't see any reason to care about this representation of functions when it comes to multiplication. And this immediately generalizes to local integer polynomial function for infinite subset, any infinite subset. And the cardinality of lip of x from this construction is continuum. All right. Let's talk about some properties specifically right now of locally integer polynomial functions on Z. First of all, obviously, Z of x is contained in it. It's a ring, a subring of the ring of all integer valued functions on Z. It is closed under also under composition, shifts, and left discrete derivative, right discrete derivative as well. So if you have f, a lip function on Z, then f of x minus 1 is also there. A third statement is very easy but important. If your function is 0 for an infinite set of inputs, then in fact it's just a 0 function. It just follows from this a minus b dividing f of a minus f of b. Because if you fix a and make b run through that infinite set, f of b is 0, so you get a minus b divides f of a, and a minus b could be arbitrarily large, so f of a has to be 0. This has consequences. This ring is a domain. Obviously, the product is 0, at least one of the function is 0 infinitely many times. Units are plus and minus 1. Again, if it's a unit, then what you mean, you have the product of two functions equals to identically 1, so one of those we have to take 1 infinitely many times or minus 1 infinitely many times. And one more of the same kind, if absolute value of f of x is prime for infinitely many x, then f of x is an irreducible element in this ring. Because if it's a product of two, then one of those would infinitely many times take value 1 or minus 1. So it would have to be 1 or minus. And it's easy to conjecture that the converse is true, but is completely out of reach, which I'll point out in a moment. Because it actually implies that every integer polynomial irreducible with content 1 takes infinitely many prime values. A big question, I mean, whenever these days you get a ring, a commutative ring with identity, you would ask yourself, is it Noetherian? And I don't know. I suspect it's not, but I don't actually have a proof of that. And I mean, it sits inside. Paul?
I was gonna say, I mean, so you're familiar with NYNTS, so polynomials with rational coefficients that take integer values.
Yeah, it's a completely different object, actually.
Okay, okay.
Yeah, I mean, yeah, I am somewhat familiar, not really.
Yeah,
but this is a completely different object. After all, you know, NZ, I mean, that is countable. This is uncountable.
Right. So NC is countable. Right. So, but I was just wondering if maybe, I mean, so NZ is not Noetherian, so maybe it would kind of the
Yeah,
proof
you see,
they use
the way I think, the way I think why it's probably not Noetherian, of course, it sits inside an obviously non-Noetherian ring of all integer valid functions. That's obviously not Noetherian. You just take the ideal of functions which are 0 for large enough inputs. Something like that. Yeah. Actually, is that right? No. Let me think about that. Yeah. 0 for large enough. I think that. Anyway, that is obviously not Noetherian. On the other hand, it contains z of x, which obviously is Noetherian, but it's somewhere in between. How large is it? Well, it's actually not close to either, so to speak. You will see from the further discussion why there are kind of reasons to believe that it might be Noetherian, which would be actually great, but I doubt. Now, let's talk about more properties of this, now using the full strength of the Lip condition. Here's a generalization of this story taken infinitely many zeros. Suppose we have an infinite sequence of x such that f of x grows slowly, at most polynomial. Then, in fact, it is a polynomial. So that's, of course, a serious generalization of having infinitely many zeros. Here is the idea of the proof. Let's just say x is the set of these inputs where the function is small. Let's take d plus 1 elements in x. Actually, you don't even have to take these in x, just anywhere in z. And suppose g of x is an interpolation polynomial, so its degree is at most d. Now, for x prime in x, and here it is essential that it is in x, we can say that f of x prime is g of x prime plus some number that depends on x prime times the product x prime minus x sub I for x sub I in our finite set. And the thing is, the left-hand side here grows as x to the d. G of x prime also grows at most x to the d. But the product grows like x to the d plus 1. X prime to the d plus 1, I should say. So it's going to grow faster, which means for large enough x prime, a has to be 0. So for large enough x prime in x, f of x prime is equal to g of x prime, where g is some fixed polynomial. And so the difference has infinitely many zeros, so f is just g. Okay. Any questions for that? So as a result, if you have f of x, which is irreducible in z of x, it is irreducible in Lz of x, because if you write it as a product of polynomials, well, they would actually grow slowly. So sure enough, And also z of x is algebraically closed. Again, because z of x is algebraically closed, and if you have any algebraic equation, the solution will have to grow slow. All right, can we improve on that? So let's actually discuss basically the growth properties of the functions f that are local integer polynomials but not integer polynomials. And here is the proposition. If we have any increasing function, we can cook up f of x, which is lip but not integer polynomial, such that absolute value of f of x is less than absolute value of x to this potential very slowly increasing tau of absolute value of x for some infinite set of x. The idea of the proof, I mean, there isn't much to it, really. We just take the sum, I from 1 to infinity, and here we take the product of x minus j for absolute value of j less than or equal to c sub I. And we just take the sequence of c sub I to grow really fast. Then at x, which is c sub k, the only terms here that would not be zero would be products of x minus j for absolute value of j less than or equal to c sub k minus 1 and previous c sub i's. So there are very few of those, and they're small if c sub k grows fast, and we can make it grow as fast as we want. So that's basically the proof. So we can't improve that. So essentially what that means, more or less, is that for a given function which is lip but not integer polynomial, if you look at the minimum of absolute value of f of x for absolute value of x up to c, this cannot grow polynomial, but it can grow just slightly faster than polynomial. That's a minimum. What about the maximum? Can we do better? The answer is yes, we can do better. Precisely what is the optimal growth? I don't quite know, but you will see this result. So suppose we have a lip function on z, and for all but finitely many x, the absolute value is less than 2 absolute value of x minus 1 factorial over 2 to the same power. Then f is in fact an integer polynomial. Okay, this is the idea of the proof. We exhaust z by segments of the form minus n and minus n plus 1n. In other words, we go 0, 0, 1, minus 1, 0, 1, minus 1, 0, 1, 2, minus 2, minus 1, 0, 1, 2, and so on. We'll look at the interpolation polynomial for our function on these subsets. Every time we increase, and we just add one more point, either our interpolation polynomial stays the same, or we add a term which has maximal possible degree. And since basically if our f is not in z of x, then that means that infinitely many times we will have to increase the degree. We will have to increase the degree, and actually we will get, for infinitely many of these segments, we would get polynomial of the maximal degree. And now we have a little lemma. If we have a polynomial with integer coefficients of degree d, and you take d plus 1 consecutive integers, well, here it's written from 0 to d, but actually, of course, you can shift. then and at least one point there, the absolute value will be greater than or equal to d factorial over 2 to the d. And so we will just apply that lemma to these subsets. We will be able to do it infinitely many times. Now, the lemma, the proof is very easy. This is where we use the discrete derivative. We take the discrete derivative of f. So the first one will be f of x minus f of x minus 1. And if we know the values of f from 0 to d, now we know the values of the derivative from 1 to d. Second derivative we know from 2 to d, and so on. The d's derivative will just get one number at d. But this number is nothing else but d factorial times the highest coefficient of that interpolation polynomial from 0 to d. And we assume that our polynomial has degree d, not smaller. So that's going to be a non-zero integer. So d factorial times a non-zero integer. On the other hand, every time we differentiate, we take the difference of values. So by triangle inequality, the absolute value of each derivative is less than or equal to twice the maximum absolute value of the previous. So the d's derivative, that number that we get would be at most 2 to the d times maximum of absolute value from 0 to d. So that proves the lemma, and that proves the theorem. Now, here's an example. You just take alternating sum, I from 0 to infinity, minus 1 to the I, times the product x minus j, absolute value of j less than or equal to I. And for all integers z, we have an equality that absolute value is less than or equal to q absolute value of x minus 1 factorial. I am a bit concerned with this at 0. Maybe x should not be 0 anyway. It doesn't matter. For a large enough x, that's going to happen. So that is what this example shows, that apart from potentially this 2 to the power on the bottom, we got the correct, we cannot improve our result. Any questions for this so far? Now, this is basically the content of my recent preprint on this that I submitted to integers, and it would be of some interest, but relatively small interest, I think, if not for some other things. So what I'm going to talk about is something that is not yet published, but I see a lot of potential here, kind of showing that this is indeed an interesting object. And this has to do with the notion of lip continuation. You're thinking analytic continuation, and you're correct. That is the analogy that I'm trying to explore. Suppose we have two subsets of z, x inside y. Let's say they're infinite. Then the restriction of lip function is always lip. For that, infinite or not infinite doesn't matter. In the other direction, if we can extend lip function from x to y for infinite x, this would have to be unique. Because if you have two functions on y that take the same values on x, the same argument as for functions on z that take infinitely many zeros, just function on y, take the difference. Because infinitely many zeros, there's got to be a 0. And so in this situation, we'll say that such function on y is the lip continuation or lip extension of f from x to y. Okay. A basic question. You have a lip function on x, and you try to extend it to, say, y sub 1 and to y sub 2. Suppose you can do it. Can you extend it to their union? this has to do with basically the union being, I mean, in a complex variable world, it has to do with the union being simply connected or not. So as an example, here on the left, you can define a function, say square root of x on this little wedge, and then you can analytically continue it to c without 0 without the red ray, the positive part of the imaginary axis. And you can also analytically continue to the complement of the green ray, but not to both. You cannot analytically continue to the entire c without the origin. So the question is, can something like this happen with lib functions? Yes, it can happen. In other words, the answer is no in general. It can happen. In fact, there are counterexamples where x is as large as all even integers, and say we can extend it to by adding a point 1 and by adding a point -1, but not to both. However, if x is large enough, and I believe the correct answer is x intersects infinitely with every arithmetic progression, which would happen in particular if x has density 1, but it doesn't have to have density 1 for this to happen. So to prove this, I mean, I'm not going to go into the details, but I'll explain some of the ingredients. One useful ingredient, of course, I don't claim really originality here. Interpolation of polynomials has been studied and well understood for centuries, at least. Exchange formula. Suppose we have x, which is a finite set now, and a and b are 2 more points. Let's see what happens, what's the relation between interpolation polynomial for the function f on x and a and x and b. Well, their difference should be a multiple of the product of x minus z for z in x. And by the degree consideration, it has to be a constant multiple. But actually, what's important is what this constant multiple is. It is c times a minus b, where c is the highest degree coefficient for the interpolation polynomial for x together with both a and b. The proof is really easy if you just compare interpolation polynomial at x union with a and b and x union with b. The difference is that coefficient c times x minus b times this product x minus z for z in x. You do the same thing for a instead of b, and you subtract, and you get the formula. Basically because x minus b minus x minus a is a minus b. A consequence of this is that if you have this x and a and b, and the big interpolation polynomial for the whole set is not integer, but restrictions to things without a and without b are integers, then this c times a minus b is in z, but c is not in z. Any questions so far? Okay. Here's an example. So we start with basically just 3 values. X will be just 1.0. A is -1, b is 1. And the polynomial is x times x plus 1 over 2. Now, technically, I could have actually started with x being empty and the polynomial being just x over, let's see, I would say x plus 1 over 2, but this is simple enough case anyway. The value is basically 0, 0, and 1. So when you restrict to just inputs minus 1 and 0, it's a 0 function. And to 0 and 1, it's a x function. But overall, it's not an integer polynomial. It's a finite example, but the thing is we can grow it. We can add one by one all integers that are even. And what do I mean by adding this? I mean, I can, so given an even integer, I can find a value here such that the interpolation polynomial for this x and a and this new value is integer, and x and b, a new value, is integer. And I then add it to x, and I can keep going. And at the end, you would get a lib function, a non-lib function, and even integers together with minus 1 and 1, such that if you throw out 1, you get lib function. And if you throw out minus 1, you also get a lib function. I don't want to go through the details, but at the end of the day, it works because a being minus 1 and b being 1, for even x, the greatest common divisor of x minus a and x minus b is 1. And that's what allows us to do it. But I want to point out that we cannot extend to odd x. Indeed, suppose we can extend to some x. And, well, I claim even if you try to do it right away without doing any other extensions, it won't work if x is odd. You see, suppose you have these values, 0, minus 1, 1, and you add some x. Then f of x must be multiple of x times x plus 1. Because your function just look at minus 1, 0, and x. At minus 1 and 0, f is 0. So your function must be, your polynomial must be a multiple of x times x plus 1. But f of x minus x has zeros at 0 and 1. So it's a multiple of x times x minus 1. An integer multiple. I mean, at that x. And so f of x over x is going to be some integer times x plus 1, but also 1 plus another integer times x minus 1. If x is odd, this cannot happen. We have even, equal, odd. And basically, this is the phenomenon. I mean, this is the explanation why this phenomenon of not being able to extend to the union cannot occur if x is large enough. Now, I don't know if that is if and only if condition. I think it probably is the case, but what's going on here, kind of intrinsic to this, I want to define this object, which is at the core of these considerations, actually. You see, when we try to understand this lib continuations, we end up dealing with functions that are not lib, but their restrictions to certain subsets are lib. So how to understand non-lib function? Function is non-lib if there's a finite subset in which it's not given by an integer polynomial. Well, we can try to remove one of those inputs to see if we can make a smaller subset that proves that our function is not lib. And we can do it until we get stuck. We have a finite subset, so that interpolation polynomial for our function in this subset is not integer, but if you remove any point, it is integer. And I'm going to call such subset a circuit for the function f. The notation, the terminology is borrowed actually from the theory of matroids, but we don't get a matroid here for, we just get a simplicial complex if you have a function, not necessarily lip, and you look at finite subsets for which the interpolation polynomial is integer, those subsets naturally form a simplicial complex. And in matroid theory, the circuit stands for quote unquote smallest linearly dependent set of vectors, or rather its matroid generalization. So here is the lemma that gives a general structure of circuits. Suppose X is the circuit for F, then, well, we know that the interpolation polynomial, by the way, I will denote this F sub X of X, that's interpolation polynomial on a subset. I should have said it before. Then it's not just a non-integer polynomial. Actually, it has the maximal possible degree, and the highest coefficient is not integer. And if D is the denominator, well, in the simplest terms of this coefficient, then all elements of X are in fact congruent modulo D. Now, the proof is very simple, actually. Again, it's related to the exchange formula. In fact, again, we just compare the interpolation polynomial on X and an X without some A. And the big interpolation polynomial is the small one, which is in Z of X, plus some constant C times the product X minus Z. So C has to be not integer, not zero, and in fact not integer, for the big polynomial to be not integer. So that's the first part. For the second part, from the exchange formula, which really comes from the first part applying to A and B and subtracting, we get that the difference between the interpolation polynomials when you remove 2 points is basically C times A minus B times some integer polynomial. And so because all of these are integer polynomials, C times A minus B must be in Z. And so denominator D must divide A minus B. All right, here are some examples of circuits. The simplest one, a two-point circuit, is you take A and B, and A minus B does not divide f of A minus f of B. So f of A and f of B are integers, so when you remove one of the points, it's all good, but together, interpolation polynomial is not integer. A more sophisticated example, X is minus 2, 0, 2. And I write polynomial as 1/2 X squared, so I really mean that the values are 2, 0, and 2. And so on minus 2 and 0, the polynomial is minus X, and minus 2 and 2 is just 2, and on 2 and X, 0 and 2 is just X. One can also do minus 4, 0, and 4 for the same function, for example. What would good in that example is that the denominator is 2, but X minus X is actually 4Z. So X minus X must be contained in denominator times Z, but it doesn't have to equal. What I don't know is the following. Given any set of any finite set in some non-trivial arithmetic progression, does there always exist a circuit? I just haven't thought enough about this. I'm pretty sure I can figure it out. Either it is true or there should be a counterexample. All right, any questions about the circuit? So basically, that's kind of all I know. So let me discuss what's next, because there are actually at least 3 different sets of questions related to this. Some are easier than the others. So there are these topological aspects. How far can we push the analogy of analytic functions? And well, the one thing about complex analytic functions is that they form a sheaf, which, modern algebraic geometry, not so modern anymore, idea of how local objects should look like, so to speak. And well, lip function on subsets of Z form what's called a pre-sheaf, which is a fancy word of saying that a restriction of a lip function is lip. And given a pre-sheaf, there is a canonical way to construct a sheaf out of it called sheafification. And theoretically, we can always do that, but in reality, you would want to have control of it. For example, maybe, just maybe, if you're talking about sets that in certain topology are not connected, well, the sheafification maybe is just to take the direct sum for the connected component. Now, what topology are we talking about? There are quite a few, and I don't know which ones are more natural. Z has cofinite topology, so open sets are empty and complements of finite. Density 1, open sets are empty and density 1 sets. Profinite, the basis of open sets are the arithmetic progressions. There is Golomb topology, which originally defined on N, but can also be defined on Z, which goes like this. It is, again, the basis for it. You take progressions of the form dx plus b, where x is a natural number, where greatest common divisor of d and b is 1. So it's greatest common divisor of the first term and the difference is 1. And it makes good sense on N, or if you talk about infinite progressions on Z without 0, you don't want to include 0. It's actually a very interesting topology and goes back to the 50s. I think, in fact, someone named Morgan Brown gave a talk in like 53, I think, some AMS meeting or something. And it's all in the 50s. Golomb was also in the 50s. And what's nice about this topology, so the set is countable natural numbers. The topology is Hausdorff and connected, which is very different from, say, profinite topology, which is Hausdorff, but very much not connected, or cofinite topology, which is connected, but not Hausdorff. And Dirichlet's theorem about primes in arithmetic progression actually suggests that primes are dense in Golomb topology. Now, the Kirsch topology, I think 70s, is a variation of the Golomb topology where the difference is only supposed to be square-free. And this has extra distinction of being locally connected. Golomb topology is not. All of these topologies, I would want to know. I wonder what happens when we consider the sheaf theoretic properties of lip functions on open subsets in these various topologies. And I want to make sense of what it means that a subset is simply connected. Ideally, Z, I want it to be simply connected, which kind of it looks like it is from those considerations. I want to be careful. The answer depends, of course, on the topology considered. And I doubt that we can talk about the non-commutative phi sub 1 of x, but maybe the commutative h1 we could realize, or maybe its profinite completion we could get. And just, the kind of simpler topological questions, given any function we have a simplicial complex of those finite y such that restriction is integer polynomial, we can take cohomologies of that. I mean, what can we say about this and things like that. And the notion of a circuit will play a key role in all of these considerations. All right, that's one kind of question. There are two other kinds of questions. I had hope at some point that this is related to the Lafontaine equations. I still have hope, but I couldn't get it anywhere. Suppose we have, say, a couple or n tuple in general. Let's say just a couple, x sub n, y sub n. We have infinitely many of those. Can we find x maybe very thin in Z and non-constant pair f comma g of Lip functions that only take values among these infinite subset of pairs? One would think, well, probably no, but I cannot prove it. I don't have an example where the answer is no. Now, if the answer is yes, that would be really good, but that means if x sub n, y sub n is a set of solution of the Lafontaine equation or system that has infinitely many solutions, now it actually has a solution in Lip functions. And it's theoretically possible that while the answer to this question 1 is negative, if you restrict this to set of solution of the Lafontaine equation, the answer is positive. But I don't know it. I don't even know what the answer is for the set of solution of the Pell's equation, x squared minus 2y squared equals 1. So good questions, but no answers. Now, algebraic properties. I already asked if Lip of Z is Noetherian. What about other x, say infinite x? Of course, finite is not interesting. They're all Noetherian, not interesting. For all I know, for all infinite x, it might be Noetherian. Maybe one can construct x for which it's provable. For all I know, this wouldn't be Noetherian. Maybe one can construct x for which we can prove it's not Noetherian. Maybe I couldn't. To what extent can one recover x from the ring? There are actually two questions in one. If the Lip of x is given as a subring of all integer-valued functions, I believe one should be able to recover x. I don't have the details yet, but I think it should be possible. If you only think of it as an abstract ring, then there is no hope, because you could have shifts of x or minus x instead of x that would produce an isomorphic ring. But maybe up to that, it is possible, but I have no idea. And so on this happy note, I just want to say a big thank you to everybody.
Thank you. Thank you, Alexander. So it's actually very interesting to see like a new subject, right? That's really interesting.
That's right.
And the problems at the end, especially the Lafontaine questions, are extremely interesting.
Yes, but I couldn't get any inroads. I mean, what is true for this Lafontaine question, you can get arbitrarily large finite sets with integer interpolation polynomials, but that's not the same thing.
Right.
Cynthia, you have a question?
Other questions for our speaker? If not, thank you again. That was very nice. Very nice.
Thank you.
Let's see. Next week, we have a speaker from Rutgers. Who is it? Next week. Yes, Quentin Dubrov, who is going to talk about a more classical question, which goes back 100 years or so. And it's quite shocking when you can say, here's a question of Erdős that goes back 100 years. But because it means it's one of his earlier questions. Because I think he was born in 1913. So it means when, no, it couldn't be 100 years. 1930s, maybe 90 years. On distinct subset sums. Very nice. So I'll see. Alexander, can you close your screen share?
Yeah, that's what I'm trying to do right now. Okay. Okay, yeah. Okay, managed.
Okay. At least where I am, it's a beautiful day. So
Same here.
I'll take a walk to my front porch and get the mail. That's my. Anything else before we go? If not, I expect I will see some of you next week. And enjoy the nice weather, everyone.
All right.
Thank you.
Very good. See you.
Thank you, Mel. Thank you.
Yeah, thank you, David.